And here's the results of that. So it turns out that the entropy change of the surroundings can be simply described for a few cases. And fortunately, they are very general cases. So the first thing is that the entropy change of the surroundings, the rest of the universe, is proportional to the opposite of the heat that the system puts into it. So this goes along with, so typically for exothermic reactions, the system heats up the surroundings. And as we talked about before, if you increase the temperature of something, its entropy will go up. And again, remember that if Q cis is negative, that means that the system is giving off heat to the surroundings, increasing its temperature, increasing its entropy. And we also know that the degree to which the entropy of the surroundings is changed is inversely proportional to the temperature at which it occurs. We often use bank accounts as an example for this. So adding $50 to a bank account that only has $5 in it is a bigger change than adding $50 to a bank account that has $5,000 in it already. So the colder something is, the more effect, a joule of heat will have. Now, these expressions can be amalgamated together to say that the entropy change of the surroundings is equal to the opposite of the heat transferred in from the system divided by the temperature at which that transfer occurred. And if you invoke constant pressure, which is appropriate for any reaction that is done in an open beaker on a benchtop, you may recall from the first semester that under constant pressure, the heat transfer is equal to this state function called enthalpy. So at constant pressure, the entropy change of the surroundings is equal to the opposite of the delta H of the system divided by the temperature. So if we put this new expression into our delta S universe equation, we say that the delta S of the universe is equal to the delta S of the system minus delta H of the system divided by T. And the very important thing here is that we've gotten rid of the surroundings. Everything here on the right-hand side of the equation is a system quantity, and those are easy to calculate, measure, what have you. And this is, now we're getting a much clearer signpost of spontaneity. So we've got delta S universe is equal to delta S of the system minus delta H system over T, and that quantity must be greater than or equal to 0. Now this algebraically, this has changed a little bit, and we can say that so the delta S cis minus delta H cis over T is greater than or equal to 0. This is usually rearranged to the form where negative T delta S cis plus delta H cis is less than or equal to 0. You will note the change in the sign right there. And finally, this is usually written as delta H cis minus T delta S cis must be less than or equal to 0. And this, in fact, is a criterion for spontaneous processes that very importantly is in terms of system variables only and not surroundings. So this was a big deal. And this was actually a big enough deal that this quantity right here, delta H minus T delta S, is given its own name, Gibbs free energy. And it was named after, so delta H minus T delta S must be equal to 0. So the proper state functions in thermodynamics are usually typically defined in terms of their absolute values. So the original definition is just G, this Gibbs free energy, is equal to the product of enthalpy minus T times the entropy. For most processes, we're talking about changes, and in terms of changes, you get delta G is equal to delta H minus T delta S, which is a fairly important expression. And again, this is appropriate for processes at constant temperature and pressure. If the temperature is changing, we have ways to work with that. And if you grow up to be a chem major when you're a junior or senior, you will learn all about that. Now, this is named Gibbs free energy after Josiah Willard Gibbs. who was not an egotist and did not name it after himself. He just called it free energy. The Gibbs thing came afterward. Now, Gibbs is actually a pretty important story. So if you look at when he did this, this was in the mid-late 1800s. He published a roughly 200-page paper that utterly revolutionized the field of chemical thermodynamics, and to some extent is relatively unchanged even today from that form. He was also the recipient of the merely or only the second doctorate that was conferred by an American university, and the first doctorate conferred by an American university in a science and engineering field. He spent his entire life pretty much in New Haven, Connecticut. He attended Yale as a student, joined the faculty there after finishing his studies, and just sort of did his thing and published this paper. And this is an example of never being famous in your own hometown. The United States at that point in time was not a particular scientific powerhouse just because we hadn't been doing it for that long. And most of these, cutting edge research in science was typically done either in Germany or in England. And so out of nowhere, this American, upstart just publishes this paper and revolutionizes an entire field. And people wanted to know more about this. So all of a sudden, there were a bunch of these, English and German folks descending upon New Haven, Connecticut, looking for this Gibbs fellow. And everyone there had no idea. They just looked, Josiah Gibbs, that dude over there, and they would point to this person, talking to his students under a shady tree, and had no idea that one of their own, hometown folk had, revolutionized an entire scientific field. The other cool story about him, he was a hands-on enough person that he actually prescribed and ground his own glasses. Now, back in the late 1800s, glasses were not that easy to come by, but still making the lenses yourself was kind of a step up. All right, so that's Gibbs free energy. A recap. All right, so again, make sure we know the sign is here. So if delta G is less than 0, it's negative. That indicates that the process is going to be spontaneous in the forward direction. If it is positive, it's above 0, then that means it's spontaneous in the reverse direction as it is written. And finally, if it happens to be equal to 0, it's at equilibrium, which means it is spontaneous in either both or neither directions, whichever philosophical bent you prefer. So next we're going to talk about a few ways of determining delta G for a reaction. The first one is the easiest, but by far the least useful, and that is a standard delta G of reactions. So this is a formalism that hopefully looks a little bit familiar. It was just the same way that we determined the standard enthalpy change for any generic reaction. And we calculated it by taking the standard enthalpy of formation of the products multiplied by their coefficients in the equation and subtract them from the standard enthalpies of formation of the reactants multiplied by their coefficients in the balanced equation. So there is an exactly, analogous way to determine the free energy change, the delta G for a particular reaction. And if you look at Appendix J, right next to the entries for the standard enthalpy of formation of something, there is a standard free energy of formation of something. And you do, again, products minus reactants times the coefficients, and you will get the standard delta G for that reaction. So that's one way of determining the standard delta G for a reaction. The other way is if you do not have access to that table of standard free energies of formation, but you do have a standard access to standard enthalpies of formation and entropies. You can do the enthalpy change for the reaction. You can determine the entropy change for the reaction, and then plug into this equation and also get the free energy change for the reaction. So that's two ways if you have access to and this is for, again, standard conditions. So this would be pure liquids, pure solids, solute species at 1 molar, gaseous species at 1 atmosphere, And it's not technically part of standard conditions, but they also typically are tabulated or apply at a temperature of 298 Kelvin as well. But these are not interesting at all because it's only at standard conditions. So let's talk about what is a more interesting thing, which would be how do we determine the direction of spontaneous change for a reaction with any set of concentrations or pressure and not just standard concentrations. Because think about it. Even if you start with exactly, 1 molar or 1 atmosphere of all your products or all your reactants, as soon as the reaction occurs, you are no longer at those conditions. And what you don't know, but do know now, is that the free energy of a reaction depends on its composition. It actually changes as you progress from pure products to pure reactants. So let's put that in cartoon form. So you can think of free energy or Gibbs free energy as chemical gravity. Now, for gravitational, so imagine, I don't know, this is top of Sandia Crest, bottom of the Rio Grande, and we're going back up a little bit to the West Mesa. There is an equilibrium position in this valley where anything that starts on any part of this hill will end up at the lowest part in the Rio Grande. Whether you start from all the way up here, whether you start from here, or whether you start from here or here, but your gravitational potential depends on your height. And it's at a minimum right here at the bottom of the valley. So the same thing goes for free energy. Now, in this case, the overall process, the pure reactants are higher in free energy than the products are. But it turns out that that is not, neither one of these represent the lowest point, the lowest energy that this mixture of reactants and products can adopt. And it turns out that in many cases, the lowest energy composition is somewhere in the middle. This is the equilibrium mixture. So whether you start from all reactants, as you proceed, you're going to keep going downhill until you get to this point. Or even if you start with all products, you're going to go downhill until you get to this point. And at that point, everything is uphill. Mother Nature is lazy slob, and you stop right there. This is why most reactions are equilibrium processes. They do not go to all products, or they don't stay at all reactants, but rather settle somewhere in the middle at an equilibrium mixture. All right, so here's what my picture looks like, just with the chemistry version of it. So the idea is that the free energy of a chemical system changes with its composition as it transforms from a mixture of, let's say, all reactants to all products. The free energy is going to change basically continuously with each little minuscule change in concentrations of products and reactants. And depending on the actual reaction, the equilibrium position, the valley, could be pretty close to all products. It could be, so that would be a product favored equilibrium. It could be somewhere around here where it's pretty close to the reactants. That would be a reactant favored equilibrium, and or in this case somewhere kind of in the middle. And the idea is that we would like to be able to determine the free energy as a function of the composition. So, if you plug in these concentrations, you get this number. If you plug in these concentrations, you get this number, and so on and so forth. And then you could figure out where that bottoms out, and that would tell you what the equilibrium composition is. And it turns out that that's actually not particularly difficult to do. So what's the relationship between the free energy of a reaction and its component concentrations? And so for a generic reaction, AA plus BB gives us CC plus DD. We have this expression here. So here it is. And this is kind of a common thing in thermodynamics, that you determine, and just so you know, the Q here is the reaction quotient that we talked about in the equilibrium chapters. And it's just going to be the concentration of the products raised to the power of their coefficients divided by the concentrations of the reactants raised to the power of their coefficients. And this is a common thing in thermodynamics that you talk about a free energy in terms of the free energy change expected under certain conditions with an adjustment, in this case, the reaction quotient. And so then this is the free energy change under those specific conditions. So again, you can, using tabular data, you can figure out the expected free energy change for the standard conditions. And then this is an adjustment for the conditions that you are dealing with right then and there. And this ends up being a fairly powerful expression. And also allows you to do something else that's pretty interesting. Interesting here being, of course, kind of subjective. So let's talk about a system that is at equilibrium. So by that definition, the reaction quotient is equal to the equilibrium constant. So the expression that we just had actually is delta G equals standard delta G plus RT ln of K. We're just substituted in the equilibrium constant for the generic reaction quotient. And if the system is at equilibrium, this value, by definition, is 0. It's at a minimum. Now, if you examine this middle part of the equation, if you know that these two add up to 0, then that means that they must be opposite, so that the standard delta G is equal to the negative RT natural log of K. Or if you will, if you rearrange it just a little bit, that K is equal to e to the negative delta G standard over RT. And this is actually a new way to calculate the reaction quotient K. Now, a couple of things to note here. First of all, we're going to use Kc for solutions and Kp for gases. The other thing is that while this is in fact the ideal gas law constant, you want it to be in the joules per mole per Kelvin version of it. So in this case, it's going to be 8.314 joules per mole per Kelvin, and not the 0.0821 liter atmospheres mole per Kelvin that you're used to with the ideal gas law. So with all of that, I think we're just going to work through an example that hits the last couple of relationships that we just talked about between standard delta G's, generic delta G's, K's, and Q's. So do your finger exercises because we don't want them to cramp up on you.